Season's greetings, everyone. Today, we are going to be talking about
the periodic table of elements, and this is an easy S tier for us. Really no questions about it.
If you just take a look at the periodic table, it looks great. I mean, there's a lot of information here that we can use as chemists, about electronic structure. There's periodic trends, there's masses. But what I really care about is the letters. The letters. And specifically how we can combine the letters to make words, and how we can combine those words to make funny phrases and sentences. If you've ever been in a science class or a chemistry class, more specifically, you will have seen decorations that are just screenshots of the atomic symbols pasted together to form words. And, that's great. I'm a fan of this. As the designer, your job is really easy. Screenshot, 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 put together, you're done. Like, no thinking is involved, except you have to figure out if the phrase or word you want to display can be spelled with the atomic symbols. Because if it can't, you have to go back and find a different phrase. And so what I'm going to be doing today is generating the once and for all list of every single word that can be spelled with the atomic symbols as a resource for all of you to use if you ever want to design decorations for the chemistry classroom, because I sure do one day. Right, so let's just get started. We have to lay the...
How would you summarize it?
Just speaks for itself.
We're going to consider a word valid if we can spell it by taking the atomic symbols exactly as they appear on the periodic table and combining them. We cannot alter the atomic symbols in any way. We can't create any new atomic symbols. And we have to spell the word as it is exactly, no adding any extra letters in. And these are all sort of examples that I have observed personally. Blasphemous examples of cheating, of disgraceful acts against chemistry and against the periodic table. And that's really what I care about preventing. Of course, this is going to be case insensitive, so we don't care if it's upper or lowercase. We also have to consider the very difficult question of what is a word. Specifically, what is an English word? It's a pretty interesting question that pops up in a lot of different places. But I really don't care about answering it. I'm trying to get as many words as possible in my search. So I just went and found the two biggest word lists that exist as text files that I could find, and I just combined them to use what this video will consider every single word. Okay. So let's try to predict something. Let's, have a look at the periodic table and see what we can see. You should instantly notice that there's two different kinds of atomic symbols, which are singles and doubles. Single has one letter, a double has two letters. My gut instinct, as well as yours, my dear educated viewer, would be that the singles would be much more useful than the doubles. And I wanted to take a little bit of time at the beginning to put some numbers to this. So basically what I've done is I've taken every single letter and I've sorted them into letters as singles and letters as doubles. The letters as singles exist as singles on the periodic table, while the letters as doubles exist as doubles on the periodic table. And basically we can go through and see how many 2 and 3 letter combinations we can make out of each letter of the alphabet, and we can see that the letters as singles make about 3 times more 2 and 3 letter combinations than the letters as doubles, which I think makes a pretty good case for why we would predict that they would be more useful. Okay, so you might have noticed when we talked about the lass versus the lad that we were missing 2 of our good friends. And if you look on the periodic table, you'll also notice that we're missing 2 of our good friends, the J and the Q. which is, it's pretty sad, really. We can just never spell any words with the J or the Q in them. Realistically, it's only 3% of the words that we're really missing out on, which is really not a big deal in the grand scheme of things. But, it still makes me a little bit sad on the inside, I guess. Right, so let's talk about...
Okay. Stafford gather time.
So we have a list of all of the words that we are considering in a text file. We read them all in. And basically, we look through them. So we have to check if the first letter exists as a single on the periodic table, and if the first two letters exist as a double on the periodic table. If we find that either a single or a double fits, then we just get rid of that part of the word and continue the procedure on the rest of the word. This continues until we run out of word, which means the word would be considered valid, or until we find that both a single and a double don't fit, in which case the word is invalid. And I wanted to just show this nice example that I made to bring in a very interesting complication that you can spell one word multiple different ways. And this occurs when both a single and a double fit. Really, the hardest part of the code is keeping track of all of the different spellings and then outputting them so that they don't look ugly and terrible. We're just going to start getting into
Position Black sacrificed
The Rock!
sort of the fun facts section of the results. So, feel free to whip these out, towards your crush, at the dinner table, or after someone gives you a compliment that's just a little bit too nice. Did you know that the longest word you can spell with the periodic table is non-representationalism, which is 22 letters long? That's crazy. So yeah, non-representationalism. Let's have some fun looking at this word. So non-representational art represents nothing but what the artist intended it to represent. So it's like the kind of art that everyone hates, basically. Or that a lot of people do. A lot of men do. Sorry boys, if you're watching. Yeah, so some of the artists I found when I was looking into this were Kazimir Malevich, Jackson Pollock, and Mark Rothko. If you're a hater of this kind of art, have you ever considered not being that? I do want to say, I understand. It's easy to hate. This takes, no skill. How am I supposed to understand what it means? And, that is true. There is a slightly higher barrier of entry to enjoy it. But just, learn about it a little bit. I'm linking a video in the description for you guys to go watch. Learn about some modern art. Enjoy some modern art. And hopefully gain a sense of appreciation for it. There's actually 3 words that tie for having the most number of spellings, which are innocuousnesses, non-euphoniousness, and pneumonoconiosis. These 3 words can be spelled 48 different ways, which is way more than I thought we were going to get. And also, these words are just awesome. Here's half of the spellings of innocuousnesses, and here's the other half. We'll spend a lot of time later trying to understand this pattern. So we ended up spelling 59,402 words, which gets us to spelling about 15% of words, which feels alarmingly correct. The warm and fuzziness feeling is off the charts when I say that it's 15%. Yeah, we're going to start getting into the sort of
Look at this graph!
section of the results, and that's really all science is look at this graph. Please validate me because I spent way too long doing this. Here's sort of things that we're going to talk about These are mostly just random questions that appeared in my head that I thought would be interesting to discuss. So earlier in the video, we made these graphs to talk specifically about the letters as singles versus the letters as doubles, and why we thought the letters as singles would do better. So now we can check to see if our intuition was correct or not by calculating the letter frequency. So we look at every letter, we count up how many times we see the letter that goes on top, and then we count up how many letters we see total. I'm just getting rid of the J and the Q here because we just don't care about them. And we get these graphs. If we divide the graphs by each other and subtract 1, we can find the relative frequency change between the two lists, which is this graph here. It looks pretty good. Obviously, it's been sorted pretty nicely by the letters as singles, mostly increase in frequency, and the letters as doubles mostly decrease in frequency, which is what we were hoping for. But obviously, there are some exceptions. What's up? It's me from the future. I may or may not be interjecting more, but if there's an explanation that I think is unsatisfactory, I'll be here. What we have yet to consider about this graph is how useful these two letter combinations actually are. You can imagine that the vowels would prefer to be with the most common consonants. So what we can do is isolate the vowels and count up how many twos they have where the other letter is one of the 5 most common consonants. Those consonants being SN, RTL. And if we do that, we see actually that A has the most twos in this category, which is why we see an increase in its frequency. And now this graph doesn't perfectly explain the frequency changes. For example, the O has the least number of twos in this category, but the E is actually the vowel that takes the largest dip. Some of the most common suffixes involving the E are ED, ER, and EN, all 3 of which we don't have access to. Hence its decrease. Now we can do the same with the consonants. We would expect the consonants to want to be with one of the vowels. So we can isolate the consonants and select only the twos in which the other letter is the vowel, and we see this graph. Now this graph does pretty well map onto our frequency change. A lot of the consonants with the fewest number of twos that have a vowel take the sharpest hits. For example, the D and the X both take extremely large hits because they have so few of these kinds of twos. The R is another anomalous letter whose frequency change is nicely explained by this graph. We can see that it much more similarly compares to the letters as singles than the letters as doubles. And then the other anomalous one to point out is the Y. And of course, the most common place for the Y to be is the suffix ly, which of course we don't have. And finally, I want to talk about the Z. There's a tiny little gap between the Z and a tragic demise. There's actually 4 words keeping the Z from dropping out of the alphabet entirely. That makes sense. If you look at the periodic table, what Z doubles do we have? ZN and ZR. Completely random, insane letters for the Z to be with. Which words exist that have these letters in them? You're about to find out. We have arzronite, which is a type of mineral. We have Hezron, which is a biblical name, and Hezronites. And my personal favorite, Biznagas. Biznagas. Biznagas? You know, I'm pronouncing these words how I feel like I should as a white man from the suburbs of America, so forgive me, I guess. So if we do some more general results, here's some math for you guys to look at. The takeaway is that the ratio of the frequency of the letters as singles to the frequency of the letters as doubles increases 1.5-ish times in our valid words list when compared to the total English language. Now we're going to talk about which atomic symbols are most useful for building English. Before we get into this graph, I do want to take a little bit of time to talk about how I generated it. So here's a word, baptism, which has 2 valid spellings. What I've done is counted the number of times the atomic symbol is seen in a word and divided by the number of spellings it has. And this is just to eliminate the reality that one word that has 48 valid spellings would be contributing essentially 48 times, whereas a word that has only 1 valid spelling would only contribute 1 time. And with this method, both words are contributing equally. That is, assuming they have equal length. If we have a look at the data, wow, no one is surprised. The S is the most common, followed by the I and the O and the N and the P and the C. And of all the atomic symbols that were used, singles account for 58% of them, which is a lot considering there's only 14 out of 118 of them. So what we can do to get a better graph is just to remove all of the singles that have counts that are higher than our highest double, which is ER. Now we can see our graph is lit up a little bit better. Yeah, there's really no surprises here either. If you look at any atomic symbol, I think you can justify why it's at the specific count that it is at. We can see from these graphs that the singles are the most favored atomic symbols, followed by doubles with a consonant and a vowel, followed by doubles with a consonant and a consonant, or a vowel and a vowel, although there's only 2 symbols with a vowel and a vowel. Obviously, some of the consonant-vowel combinations are much more heavily favored, but generally all of them have at least some uses, whereas there are some consonant-consonant combinations with practically 0 uses. Although, it should be noted that every single atomic symbol was used at least once. I have a little PSA to show now for the next part of the video. Attention, physicists. If you or one of your colleagues is currently working to create and detect the next element, please listen well. I stand before you as a humble representative of the people who design chemistry decor for the classroom. And as such, I am a man with one goal: spell every single word with the atomic symbols. Now, you might not think this goal is important, but it is important to me. And as such, you should consider adding the atomic symbol Ng to the periodic table next. Feel free to create any element name crafted around this symbol, but it is imperative that this be the next symbol, as it would allow us to spell the most number of new words. Just imagine all of the new lab decor we could include in our spaces with this addition. Glad that's over with. So let's talk a little bit more about this graph. It's not very surprising that NG is giving us the most increase because it allows us to use the ing suffix, which is extremely common. Same with ed. Obviously, that's an extremely common suffix as well. LE is a little surprising, but L is one of the most common consonants, and it took a pretty sharp decline, as we saw earlier. I was looking at this graph, and the one pattern to observe is that these doubles seem to want to go at either the beginning or the end of words. And I made this graph just to prove that. This is just a histogram that shows the position of the doubles in the word, and I created it just by taking the position of the double and dividing it by the length of the word minus 2. And so that way, if a double is at the beginning of the word, it will always have the value 0, and if it's at the end of the word, it will always have the value 1. If you think about a word that either begins or ends with a letter as a double, then you really only have one chance to get that letter in the correct spot. Whereas if you think about a letter as a double in the middle of a word, you have 2 chances to get it in the correct spot. So it makes sense that the symbols that are most advantageous to add would appear more often at the beginning or end. And this is real, by the way. We can check to make sure by looking at our frequency change between the list of every word and the list of valid words that begin and end with a letter as a double. Earlier, we mentioned that we're missing both the J and the Q, and I said it wasn't that big of a deal because we're not missing out on that many words. That is supported here. The first time the Q or the J makes an appearance is in QU, which is the 57th most advantageous symbol to add. So there's a lot of bigger fish to fry here. Okay, moving on from that to looking at how the length of the word affects the probability of spelling it. What we're going to do is we're going to take our list of all words and separate it out into lists of length 1, length 2, all the way up to our longest word, which is 31. So imagine having a bunch of different lists and getting their individual probabilities, and we end up with this graph. And you can see the black line is our 15% probability for the entire list. So you can see that the probability decreases as we get longer words, which, does that make sense? So now we get to the fun part where we get to do math. Is this what we expect? So we can reach into our bag of assumptions and pull out assume equal probability for any given letter or 2-letter combination. Making this assumption allows us to calculate the probability of a single being valid by just counting up all the singles we have and dividing by the total, and same for the doubles. And what we will do is we will take our word and we will decompose it into a number of singles and a number of doubles. We will call this a decomposition naturally, and we can use that decomposition to calculate the probability. First, we should start with looking at how many decompositions there are. So you can imagine for a 2-letter word, we can either have a single single or a double, 3-letter word, a single single or a single double, and so on. We end up finding that the number of decompositions is just the length of the word, divide by 2, drop the remainder, and add 1. That operation, dividing and dropping the remainder, is just called floor division for you non-coders out there. Anyways, we have to calculate the probability for any one decomposition, which isn't so hard. We end up having 2 sections of the formula, which is a number of permutations and the actual probability. So you can imagine arranging for our 3, which had single double, either single double or double single. So whatever our probability is, we have to multiply by 2 because we have 2 options. And of course, our probability is just the probability for singles raised to the power of the number of singles, and same with doubles. We can go through and look at 3-letter words. So we can get the probability for each decomposition and add it up to get the total probability for 3-letter words, which is 0.33. We can do the same thing for 4-letter words and get a total probability of 0.24. If we sum up the number of permutations and the probabilities for all decompositions for 4 and 3-letter words, we see that as the word length increases, the number of permutations increases and the probability decreases. If we do this for every word length, then we can compare with our observed data. So here, the theoretical graph is on the left and the observed is on the right. They look very good. Obviously, they're not exactly the same, but we wouldn't expect them to be anyways. What is important is that the trends in both graphs are essentially the same. On the left, we have a sharp decrease in probability caused by a sharp decrease in decomposition probability. And then on the right, it steadies out, which is caused by an increase in the number of permutations. Now, why aren't they exactly the same? Well, we sort of start to run out of words as we get into this region, which is why it gets kind of wobbly. And generally, I think our probability of the doubles was a little bit too small compared to what it should be. So if we considered how common each double was and scaled the probability based on that, we could get a more accurate result. The last question for us to answer: how likely is any word to have a given number of spellings? So if you graph it out, it looks kind of like this, which looks like nothing's going on. So the vast majority of words can either be spelled 1 or 2 times. But if you plot the same graph on a log scale, we get this majesty. I mean, look at this thing. It's got so much to offer to us. There's a bunch of spellings early on that take a sharp 2 magnitude decrease in probability. And then the gaps get really large until 48. Why are these ones towards the beginning so uncommon and these ones towards the end common? So we're going to formalize this in terms of spelling trees. Their size will tell us how many spellings a given word has, and they will consist of choices and branches. So here are the rules for building them. One choice can only have 2 branches. All choices must be applied to all branches, except the double branch of any choice can be removed by the previous choice, and this is called a dependent choice. And a dependent choice cannot exist without an independent choice. So let's talk a little bit about why these are the way that they are. So one choice can only have 2 branches, and that's because in any given spot in our word, we can only choose to put a single there or a double there. And since we have 2 options, that means 2 branches. The act of choosing the single or double diverges the branches. So you can see at the spot in the line, the top branch has a length of 1 and the bottom branch has a length of 2. So they are diverged by 1 letter. At the second line, they converge. So now the top and the bottom branch are exactly the same, NAC. Because they are exactly the same, any choices beyond this point in the word must be applied to both branches. You can see we're looking at a 4, which is the result of 2 2s. You could imagine adding another 2 at the end of this word to get an 8, since all 4 branches would split into 2 more branches. Or you could add a 3 at the end of this word to get a 12. Importantly, the branches of the second choice also must converge in order to spell the same word because they must have the same length. Now we get on to the most important exception, which is the double branch of any choice can be removed by the previous choice. And the reason this happens is that before the branches of choice 1 can converge, there is a second choice. Because the branches aren't the same length, it's only applied to the shorter of the 2 branches. And you can see why that is. The N is causing choice 2 to occur, but for the lower branch of choice 1, the N is already used in the atomic symbol IN. The reason the double branch is always removed is because the longer branch of choice 1 will always converge with the single branch of choice 2. So we will have the single branch of choice 2, the double branch of choice 2, and the single branch of choice 2. So a little bit more formalism, we can call the 2 the I tree because it is the result of 1 independent choice, and we can call the 3 the ID tree because it is a result of an independent and then a dependent choice. And if we add an arbitrarily large number of independent choices at the beginning or end of these trees, we can calculate their size, which is shown here. You can see the 3 is eventually extended to be our 48, which is our max. What about 2 dependent choices? If the 2 dependent choices are independent of each other, then we know that's just 2 3s, which makes a 9. However, what happens when they're mutually dependent? All we have to do to figure that out is take the 3 and add a copy of its single branch to make our new tree. Here, the single branch of the 3 is the 2, which generates a 5, since we have the 3 and the 2 together. Here, I'm showing a 3 where the single branch is the 1, which generates a 4. If we make these trees arbitrarily long, we get these sizes. With this information, we can go through each number until 48. If it's a composite number, we know that that size tree will be made up of its factors. So for example, we saw the 9 was made up of 2 3s. And if it's a prime number, it will be made of an IDDD tree, which I wrote a program to find the smallest one that would fit. That allowed me to create the theoretical minimum number of choices graph you see on the left, and we can color code our observed number of choices to make this graph we see on the right. I should note that for numbers of spellings that have 2 different size trees, that the bars are overlapping and not adding up to the appropriate magnitude. This was done to better compare the magnitudes of trees that have the same number of spellings. And because it's a log scale, taking half of any one bar will not decrease its magnitude so much relative to the others. From these graphs, we can see that generally the most favored tree for any number of spelling is the one with the minimum number of choices. The reason that the bars get so spaced out at the end is because the trees that have 6 spellings become increasingly spaced out. And I should note that I have really no idea what's going on with 43 and why it takes a sudden jump to 11, which seems insane to me, but I trust my code that it worked. If we take a look a little bit more closely at our observed graph, we can see that trees with a identical number of choices have a fairly similar observed probability. Hopefully, by looking at this graph, you start to notice a pattern within the individual number of choices. If we separate each number of choice into its own graph and plot it on a linear scale, we can see the pattern a little bit more closely. My plan is to explain the choice number equals 3 graph because there's only 4 numbers to explain. We saw that the only difference between the 4 and the 5 earlier was that the 5 had a 3 where the single branch was the 2, and the 4 had a 3 where the single branch was the 1. What we actually need to do is look at the 3 and identify why the 3 with the single branch as the 2 is more common than the 3 with the single branch as the 1. And I believe it all comes down to this extra atomic symbol here. If you look at the strings that are generating these patterns, you'll notice that the common 3 is 1 letter shorter than the uncommon 3, which will favor it because we more often spell shorter words. You'll also notice that the uncommon 3 also requires an extra atomic symbol, which should make it less probable. Now we're going to do 5 versus 6 versus 8. So the 5 obviously is a special tree, the IDD tree. The 6 is just a 3 and a 2, or a 2 and a 3. The 8 is just 3 2s. If we take a look at the minimum number of singles that we need to form each of these patterns, we can see that the 2 requires 2 singles, the 3 requires 3 singles, the 5 requires 4 singles. These trees combine to make the 8, the 6, and the 5. And so we can figure out how many singles total we need for each. The 8 ends up requiring 6 singles, the 6 requires 5, 5 requires 4, which we already talked about. Again, the shorter our word is, the more likely we are to spell it. So this seems to support the 5 because it requires the fewest number of singles. When we talked about dependent choices, we saw that they exist when a choice appears before the 2 branches of the previous choice converge. When we looked at the common versus the uncommon 3, we saw that most often this happens 1 letter after the first choice is made, and slightly less common 2 letters after the first choice was made. In both cases, we see that the two choices are very close in proximity to each other. When we think about two independent choices, they can be placed anywhere in the word and still generate the correct pattern. This explains why the 4 is more common than the 3. Because the average word length is 9.5 letters, if you were to randomly arrange two choices in a word, we would expect that they would much more often be separated than adjacent. This argument applies to the 8 as well, although slightly less strongly. We would expect at some point as the number of choices increases for this to become a disadvantage. Eventually, if you were to arrange some number of choices in your word, you would expect to see adjacent choices appear more commonly as the number of singles needed approaches the word length. So just to recap, this favors the 8 and the 6 just because they both have the ability to spread out their choices over the entire length of the word. And I'm not sure this actually favors the 8 more than it favors the 6. It's up in the air, but the point is that both are more favored than the 5 in this aspect. From here, it really seems to be very simple for why the 6 is so probable. That it has... So there's the 6 as Hannah Montana. Yeah. So yeah, that about wraps us up then for the questions that I had personally. Except there's a surprise.
Let's try this one. How do knights move?
Finale to this video. So we talked about the common 3, which we saw in wines. And it was common because the single was the shorter of the two branches of choice 1. And we talked about the 5. We didn't talk about the common 5, but I think it would be not that hard to say that common 5 comes when the single branch of the second choice and the third choice both lead into the larger of the two branches. That's the case here in sun baths. So what happens if we keep doing this? If we construct IDDD trees where the double branch is always the smallest, it's always removed. So we take the 3, its largest branch, which is the 2, to make the 5. We take the 5, its largest branch, which is the 3, to make the 8. And then we just keep doing that. And yeah, hopefully you see that these trees are forming some kind of pattern that you might know of. Dear viewer, it's the Fibonacci sequence. And it's not really hard to figure out why it shows up here. I mean, we're literally doing the Fibonacci sequence to make these trees. If you look at the Fibonacci sequence, we just take the previous number and its largest addend, add them together to make the new number, which is what we just did to make the trees. We took the 5 and we took its largest addend or branch, which was the 3, and added them together to make the 8. So this is just the Fibonacci sequence. It's here. Let's go. In the 5 versus 6 versus 8 discussion, we talked about the number of singles required to make each of those size trees. You can also look at it from the other perspective. So what is the maximum tree length that we can make with any given number of singles? Oh boy. So 1 single makes 1, 2 singles makes a 2, 3 singles makes a 3, 4 singles makes a 5, and you get the idea. It's the Fibonacci sequence again. What? It's Fibonacci sequence again. Yeah, so how do I know this is correct? And let's take the 3 singles example. So how can we arrange 3 singles in 3 different ways? Well, we can do single, 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 double, or double, single. And what does this remind us of? Of course, it is the decompositions and permutations of 3-letter words. So on top is our single, single, single decomposition with 1 permutation, and our bottom is the single, double decomposition with 2 permutations. It shows up here as well. And it's not exactly clear looking at this why exactly it shows up here, but it does. And you can make the argument that the decomposition and permutations generate the number of singles, which generate the trees. And since it's so obvious why the Fibonacci sequence shows up in the trees, then it must show up in what's creating the trees. I don't know. I don't know. But it's here. And I think that's what matters. So for the finale of this video, I would like to present an extremely weird formula for the nth term of the Fibonacci sequence that I found while trying to spell with the periodic table. Wow. There it is. I mean, it looks great. it looks crazy. Yeah, so obviously this is just our permutations formula from earlier, where we have just ND and NS defined at the bottom. These weird brackets are the floor, so we're summing over all of our decompositions and adding up all of the permutations. And yeah, it works. Put it into Wolfram Alpha, and it'll spit out the Fibonacci sequence. So yeah, that's all I have for you guys. If you're here, if you watched the video, that's cool. I just could not stop myself from making this because I just had to. I mean, it just got hyperfixated and it's game over from there, you know? But yeah, hopefully it was fun. Hopefully you learned something. Hopefully you understood everything I said. And if you didn't understand everything I said, or if you feel like I missed something or my explanations weren't clear, then just put it in the comments and maybe I'll do another one. Who's to say? I probably won't make any other videos though, but maybe I will. But yeah, that's all I think. Bye.